All right, so today we're going to get into Ka and Kb, which are the acid dissociation constant and the base dissociation constant, or equilibrium constant. So when we're talking about Ka and Kb, we're talking mostly about the Ka and Kb for weak acid, because if you think about a strong acid, if we have something like HCl, that's going to completely dissociate into H plus Cl minus, right? And so we're going to have basically zero of this left at equilibrium. And so if we do the Ka for that, it's going to be H plus, if we write the expression, Cl minus over HCl. This is going to be almost zero, or really close to zero, and these are going to be very large, so our Ka is going to be very, very large. So we don't even really bother with the Ka for strong acids or bases. We mainly focus on the strong acids, the weak acids and bases with the Ka. And the way that it works, so if we have a weak acid that's called, let's call it HA, and we add that to water, so that could be any acid, HA, and if we then try and finish, if it's an acid, it's going to donate its proton to water, so it ends up being H3O plus A minus. Okay, so then if we wrote the Ka, the equilibrium expression, it's going to be products over reactants, so H3O plus over A minus, times A minus over HA, and the water's a liquid, so we don't include that. All right. Now, I know that if I compare this to this, right? If this is a weak acid, that means that these are not going to be, it's not going to dissociate completely. It's going to be pretty low dissociation in general. And so these are going to be pretty small. This is going to be pretty large compared to these. So our Ka should be pretty small. And in fact, that's what we see. And we have a table, you have a table in the folder of the Kas for some common acids. But what you can do with this then is you can do several different things. First of all, there's rice tables that you can do. If we know concentrations, we can calculate the Ka. If we know Ka, we can calculate concentrations, and vice versa. Now, one thing to note, okay, when we go back this way, so HA would be the weak acid, A minus would be the conjugate base, and the conjugate base we can't use, so if this was if we do the reverse, HA plus H2O. Now we're talking about Kb, right? And Kb is going to be HA over A minus times H3O plus. Okay? But how do I know the Kb? Well, Ka times Kb equals Kw. So the equilibrium constant for water, the autoionization constant for water, which is 1 times 10 to the negative 14th. So if I know the Ka for an acid, then what I have to do is divide that Ka or divide 1 times 10 to the minus 14th by the Ka, and that would give me the Kb for the conjugate of that acid. Okay, so that's one way that you can go back and forth between Ka and Kb for an acid and its conjugate, or a base and its conjugate. So, if we, I'm just gonna, so let's do a problem with this HA. So if we have an initial concentration of 0.3 molar for HA, so back up here, okay? So if that's the initial concentration, and we know that the equilibrium constant, the Ka for HA, is 3.5 times 10 to the minus 7th. Okay. Then we also know at equilibrium, so this is an initial, actually let's change it up. Let's say the equilibrium, this is equilibrium, this is at equilibrium. Hold on, let's go back. This is the initial, sorry. This is our initial, and we want to know what is the equilibrium concentration for all species. So what we would do is set up a ice table or rice table. So if this is HA plus H2O yields H3O plus A minus, right? I don't care about the water because that's not part of my expression. I know that this is 0.3. I know that these are 0 initially, right? This is going to be minus X. This is going to be plus X plus X. So this will be 0.30 minus X, X, and X. Okay, so then if I'm going to plug this into my expression, I'm going to end up with 3.5 times 10 to the minus 7th equals, these are going to be on top, so that's going to be X squared on top, and then 0.3 minus X on the bottom. Now with this, because this number is very small, we can actually ignore this minus X. So you would say 0.3 minus X is approximately equal to 0.3. Okay, so then it becomes X squared over 0.3, 0.3 equals 3.5 times 10 to the minus 7th. And we could do that again if we think about sig figs, right? This is pretty much just going to be, it's going to be 0.2999997 or something like that. It's going to be so small. So then I got to multiply both sides by 0.3. So 3.5 times 10 to the minus 7th times 0.3. That gets me, I'm going to rewrite it over here, 1.05 times 10 to the minus 7th equals X squared. So then I take the square root of both sides. 1.05 times 10 to the minus 7th. And X is going to equal 3.24 times 10 to the minus 4th. So then those would be that would be my equilibrium concentration for the H3O plus and the A minus. And then the HA would pretty much just be 0.30. All right? So, I hope this helps. Let me know if you have any questions.